This video is produced as a study guide for students enrolled in the EPO 322 Diesel Engineering 2 simulation course held at Cal Maritime. This video is the first of a two-part series. The discussion will be on diesel engine emission reduction. The reading assignment for Lesson 1 is Chapter 8 and Chapter 3 out of Pounders, and also over three Burmeister Wing technical papers on their low-speed, large-bore engines, exhaust gas emission control, and Tier 3 two-stroke technology. Reference material for that related to this presentation is Chapter 3 out of Pounders, exhaust emissions and control, exhaust gas emission control today and tomorrow, and Tier 3 two-stroke technology. This presentation will give an overview of the current international regulations concerning exhaust gas emissions in the marine environment. A discussion on the composition of exhaust gas will be undertaken. Current emission technologies will be discussed in addition to those methods that are currently under development, which are improved fuel injection equipment, water fuel emulsification, direct water injection, selective catalytic reduction, exhaust gas scrubbers, exhaust gas recirculation, and scavenging air moisturizing system. Waste heat recovery and the burning of clean LNG fuel will not be covered, as they will be reviewed in separate presentations. MARPOL is international regulations, and these emissions regulations are contained in Annex 6 of the MARPOL 7378, and they have been in force since May 19, 2005. Tier 1 is retroactive to vessels built after January 2000. Tier 2 regulations come into force in January 2011. Tier 3 regulations will come into effect in January 2016 when a vessel operates within an environmentally controlled area. This reduces the NOx levels by 80% from Tier 1 across the entire speed range. Existing pre-year 2000 engines will be required to reduce their NOx levels to Tier 1 specifications. So these are international regulations that will affect all shipping throughout the world. The environmentally controlled areas at the present time are off of all of North America, Hawaii, the Baltic, and North Sea of Europe. Coming in the future, we'll be seeing that Mexico, Puerto Rico and the American Virgin Islands, the Caribbean, and Japan. So the NOx emissions, as far as Tier 1, Tier 2, and Tier 3, these were phased in over time to allow the companies to work on the problem and come up with solutions. Now, on the left hand, you can see that those are the NOx emissions in grams per kilowatt hour, and on the bottom is for the rated engine speed. Our discussion primarily today will be on the low-speed diesel engines, which are going to operate well below the 200 RPM range. So we're talking about the left-hand side of this graph. Typically today, your diesel engines for the slow speeds are going to run 76 RPM, say, up to about 125. Now, when you're looking at a comparison from the Tier 1 to Tier 3, you can see that this is a lot of reduction of NOx. In fact, it's 80%. And these regulations are just this year in 2016 have become into effect whenever you are in an environmentally controlled area. Outside of environmentally controlled areas, you will be under Tier 2 regulations. But once you start looking at these environmentally controlled areas coming in, specifically North America and Europe are some of the biggest trading partners, you're going to see that most of the ships will be coming out that are built today to meet Tier 3 regulations. So an environmentally controlled area has low sulfur mandated below 0.1% sulfur. Scrubbers can be used as an alternative to burning low sulfur fuel. We will talk about scrubbers later on in this presentation. Globally, heavy fuel oil can contain no more than 3.5% sulfur. So there's a big difference here when we're talking between high sulfur 3.5% and low sulfur, which is 0.1%. But even this 3.5% is a reduction because we were seeing sulfur in fuels as much as 5% until recent times. After 2020, globally, heavy fuel oil will not be able to contain more than 0.5% sulfur. So we're rapidly moving towards this low sulfur fuels. And these are, again, we will talk a little bit more about the SOx, but when you remove the reduction of SOx emissions are primarily tied to the removal of sulfur out of the fuel. Because of its high thermal efficiency, the low-speed two-stroke diesel engine is the heat engine currently available for vessel propulsion with the lowest CO2 emissions. These are very, very high efficiency engines, and we're talking now worrying about global warming, that you want to be able to move your cargo with the least amount of or the highest efficiency engine out there, and that currently today is the big two-stroke diesel engine. Further emission reduction can be achieved through the following methods: increasing total plant efficiency through the recovery of waste heat, improvements of fuel injection systems, electronic control of engine parameters, water emission in engine fuel, humidification of the engine intake air, which is, for Burmeister Wain, is their SAM, selective catalytic reduction, SCR, and switching to cleaner burning gaseous fuels, LNG. So when you look at this chart, and these just are kind of relative to each other, you can see that when you take a look at a large container ship compared to something as an airplane, the vessels can carry large amounts of cargo with the quite low use of fuel. And very typically you have ships bringing goods to the United States, to the West Coast, on large container ships, and then we will move that across the United States using trains, and it's a very efficient system. With the Panama Canal going with the larger locks, you may be seeing more of these container ships actually going through the Panama Canal and over to the East Coast. But again, the shipping represents the lowest production of CO2 per weight of material moved. So, emission reduction methods that are available today is fuel injection equipment modification, specifically electronic control, water emulsion, selective catalytic reduction, waste heat recovery systems. And again, waste heat recovery system, what we're talking about is lowering CO2 because we're increasing the efficiency of the plant and burning natural gas fuel. Specifically too in the United States, with the increased production of natural gas, I would not be surprised if this does not become a major influence in future for North America. In processes that are currently being developed or being adapted to market needs, Burmeister Wain has the SAM, which is the humidification of the intake air. Exhaust gas recirculation. Now, exhaust gas recirculation has been used for a long time, since probably we're talking back to the 70s, on internal combustion engines for the automotive sector. And so what we're looking at is moving that over into the marine sector. The problem comes into that, though, is that we are burning heavy residual fuels, and those residual fuels and the particulate matter can cause some problems for exhaust gas recirculation. extended combustion configuration, external waste heat recovery systems, and again, the burning of liquid nitrogen or LNG fuels. Sorry. So increasing vessel efficiency results in a general reduction of all plant gaseous pollutants. Waste heat recovery has the potential to increase total plant efficiency to as high as 60%. And 60% is, with our current technologies, about the best that any heat engine, not just the heat engine, but total through waste recovery that we can achieve. 60% is really at the top. Many older diesel propulsion engines can be modified to meet Tier 2 regulations. For the Burmeister MC slow speed engines, this would require modification of the fuel injection equipment. And in reality, what they're doing is they're taking off the mechanical fuel pumps and replacing them with electronic control fuel pumps. And then also the fuel valves themselves, they're going over into the slide valve type. Adjustment of the combustion chamber volume by adjusting the piston rod shims, and changes to the scavenging air pressure and exhaust cam profile. So for NOx reduction, we'll separate this into pre-treatment and into internal treatment. So for pre-treatment, emulsified fuel, you're going to put the fuel through a homogenizer and bring in water and actually emulsify that water with the fuel. It can be up to about 50%. And then when that water evaporates in the combustion chamber, that acts to cool down the combustion gases. And NOx is typically produced under high temperatures and high pressures. If you lower the temperature, you will lower the amount of NOx production. And again, to lower NOx, you can also change over to a cleaner burning fuel, methanol or LNG. Internal treatment for combustion, injection rate shaping, and this is interesting, and this is within the realm of the new electronic controls. With electronic fuel injection that are controlled off the computer, you can literally change the rate that the fuel charge is being pushed into the cylinder. Now with the old mechanical systems, you went to a full rate and you continued at a full rate until you had a rapid shutoff. The longer that you injected at that full rate, the more fuel that you injected into the cylinder. Well, with the advent of very high-speed solenoids and using hydraulics, the rate at which you're injecting into the cylinder can be varied to give you a burn that will produce lower temperatures and lower pressures. And this is under development right now, but it works quite well. And again, one of the things on this, you've noticed on the automotive sector that everything has gone over to full electronic control for similar reasons that we're talking about. So what you're going to see on today's engines in the marine world is everything is going over to electronic control, excuse me, and that you will see that mechanical fuel injection systems are basically outdated at this point. You can also retard the fuel injection timing. You can go to lean combustion or rich combustion, pre-chamber type combustion, fuel valve nozzle modification, and the high pressure of fuel injection. So for NOx reduction methods, for internal treatment and scavenging, we're looking at scavenging air cooling. Cooling that scavenging air charge down, but prior for it to going into the engine. And that would reduce the temperatures after the compression cycle. So typically on that, one of the major one is this humidification of the incoming scavenging air. And that will cool both ways. It actually will cool the incoming scavenging air charge, but also the moisture in that air when as you compress it and it vaporizes, taking heat out of its surroundings will cool the air in the cylinder so that your total temperatures after after compression will be much lower. And then there's water injection into the cylinder. And we'll see on the simulator we actually have this, and you can emulsify up to 50% water into the fuel. And then as that fuel is injected into the cylinder, it will actually evaporate and act as to cool the air charge. There's also methods, and Wärtsilä uses this, for direct cylinder injection. So you can directly inject water into the cylinder. And this is, again, to act as a cooling agent. And this is not a new idea. This was actually used in World War II for the high altitude aircraft interceptors, such as your Mustang or your P-38. The problem was they had such big turbochargers and their auto cycle that when they got down, so they could operate at these very high altitudes, when they got down to low altitudes, they would get pre-ignition, and they had actually water injection into their intake to lower the temperatures to prevent pre-detonation at low altitude. So it's an old idea that's coming back. Also, cycle modification and exhaust gas recirculation. Post-treatment is selective catalytic reduction, and this has a lot of promise. It has very little effect on the efficiency of the engine, and you have the most NOx reduction. Most of the other methods we're talking about are probably can be up to 70%, but with selective catalytic reduction, you can reduce NOx as much as 95%. So another method is to burn low sulfur fuel such as distillates or LNG. Now SOx, we're talking about SOx. SOx is sulfur that is turning into sulfuric acid. What happens within the engine is because you're burning this high sulfur fuel, after the combustion process it will mix with oxygen, and then as that is released into the atmosphere will combine with water and become sulfuric acid, H2SO4. And this is a primary concern as far as acid rain, which changes the pH both of our lakes and on the land. And the primary way that you get rid of it typically is you burn a low sulfur fuel. And this is what we've been doing and specifically in California for a long period of time. There is a loophole that you can also, even in the environmentally controlled areas, you can install an exhaust gas scrubber. What you're doing with this is you're taking and scrubbing the SOx and the particulates out using salt water in a after treatment. In other words, this scrubber is after your treat your exhaust gas and before it leaves the funnel. And then the problem with this, though, is unless you treat it to reduce reduce the sulfuric acid, what typically happens is they are directly putting this back into the sea. Now the sea will neutralize, because it is naturally alkaline, will neutralize a lot of this acid, but you are injecting that acid directly into the ocean. And we will talk about this a little bit more later on. So diesel engine emissions are comprised primarily of nitrogen, oxygen, carbon dioxide, water vapor, carbon monoxide, oxides of sulfur and nitrogen, and partially reacted and non-combusted hydrocarbons. Also, we have particulate material. Carbon monoxide results from the incomplete combustion due to a local shortage of air and the dissociation of carbon dioxide. Carbon dioxide contributes to the greenhouse effect and hence the changes in the Earth's atmosphere. So this gas is an inevitable product of combustion of all fossil fuels, but emissions from diesel engines, thanks to their thermal efficiency, are the lowest of all heat engines. So by using high efficiency engines, we are hoping to reduce the amount of carbon dioxide production and how that contributes to the greenhouse effect. Now, one of the things, don't think for a minute that we are not, in the marine world, a major contributor to the global greenhouse effect. We are. Modern engines, especially now the larger engines, may burn as much as 200 metric tons of fossil fuel per day. So it is a major imperative that we reduce carbon dioxide emissions as much as possible from marine engines. Nitrogen oxides are generated thermally from nitrogen and oxygen at high combustion temperatures within the cylinder, and they are of special concern as they are believed to be carcinogenic, contribute to photochemical smog formation, contribute to the formation of acid rain. Internal combustion engines primarily generate nitrogen oxide, but as much as 10% of that oxidizes to nitrogen dioxide the moment it escapes as an exhaust gas. Sulfur oxides are produced by the oxidation of sulfur in the fuel. They have an unpleasant odor, they irritate the mucous membrane, and they are a major source of acid rain. Acid deposition is a transboundary pollution problem, so SOx can be carried over hundreds of miles in the atmosphere before being deposited in lakes and streams, and also can acidify the land. The use of exhaust gas scrubbers has the potential to modify the pH of the ocean due to the use of salt water to scrub acid from the exhaust stream. I will also include a technical bulletin from the Environmental Protection Agency that was a very, very good discussion on this exact point. They're much more concerned about the rising CO2 levels in the atmosphere, that will have a much greater effect on the pH of the world's ocean through carbonic acid. So this is a concern, but again, the Environmental Protection Agency of the United States felt that the amount of acid that we were putting in the water was minor compared to that, but I'll let you read that article at your own discretion. Hydrocarbons are created by the incomplete combustion of fuel and lube oil, or the evaporation of fuel, and as far as which are unburned hydrocarbons. They can have an unpleasant odor, they're partially carcinogenic, they can irritate the mucous membrane, and are smog forming. Unburned hydrocarbon emissions however, are typically low for a modern diesel engine, specifically for electronic fuel injection. You will not have much unburned hydrocarbon emissions. Particulate matter. Particulate matter is a complex mixture of inorganic and organic compounds resulting from incomplete combustion, partially unburned lube oil, thermal splitting of hydrocarbons from the fuel and lube oil, ash in the fuel and lube oil. More than half of the total particulate mass is soot, whose visible evidence in smoke. Now, this also is a fuel issue. Clean distillates will have much, much less particulate matter than an engine burning heavy residual fuels. Heavy residual fuels with that complex hydrocarbon chain, you will have a lot more particulate matter, a lot more soot, a lot more smoke. That's the nature of the beast. And again, if we end up going into scrubbers, one of the things the scrubbers will do is remove this particulate matter from the exhaust stream, and again, scrub that out of your exhaust gas. they are planning with that then to collect that material, and which would form a sludge that you would carry on board and discharge at port. The Though, like I said, one of the things with this, burning clean fuels, specifically burning natural gas, would virtually eliminate this problem. Exhaust emission reduction. So, modification of the fuel injection system. The Burmeister Wain has developed some new, well, all the companies have, but in this we're talking more than Burmeister Wain. Newly developed fuel nozzle designs with a lower sac volume have a significant impact in lowering NOx formation while having a positive effect on combustion. And recent advances in electronically controlled diesel engines have shown that the unique rate shaping of fuel injected into the combustion chamber makes it possible to lower NOx emissions with little or no effect on fuel efficiency. So on the Burmeister Wain, on the left, that is their conventional fuel valve. In the orange, that's the needle valve. And in the blue, that's actually the injector tip, and it's seated. Down at the yellow, that extends into the combustion chamber through a hole. And you can also see where one of the injection holes where the oil would come out. But underneath that orange needle valve in the white, that is a void space. And when the needle valve opens, you're going to inject, that fills, and you're going to inject fuel into the cylinder. But when the needle valve closes, that fuel that's still left within the sac, which is that, again, that white area within the yellow tip, that is going to, fuel will remain in that area, and then it can dribble into the cylinder. Elimination of the sac volume is one of the major ways that they have accomplished reducing particulate matter. Such a small thing, but it makes a difference. And this is not specifically just Burmeister Wain. You'll see this on any of the diesel engines today, including those used shoreside on trucks. On the right is their new slide valve. Now, the slide valve is quite different. It does have a similar to the needle. This slide valve moves up and down and is pressure dependent. So when the pressure acts on the area around the needle, it will lift it up. But instead of opening a port and the fuel going down that port into your nozzle tip, it is actually a slide valve. So the oil goes down the interior, down the middle of this slide valve. So as that fuel pressure comes in and lifts up this slide valve, the fuel will go down the interior, the middle of that slide valve, and then there is a port or a hole going through the tip that will match up to a hole in the slide valve, and the fuel can go down the interior and then out into the combustion chamber. Then as that slide valve moves back down, that port is covered and fuel delivery is stopped, and there's no fuel left down within the tip. So again, this is a slide valve, and it moves up and down, and there's a port in the slide valve that matches up with a port in the tip, and fuel can, once it lines up, can go directly into the combustion chamber. But as that slide valve moves back down, that port is closed off and the fuel is shut off. So there's no remaining fuel and there's no sac volume. Now this has been very successful for them and has significantly reduced particulate matter and has really contributed to better combustion in the cylinder. So you'll see on this that even the older vessels are being retrofitted with these slide type fuel valves. They've been very successful. Now, This is a diagram of the Burmeister-Wain modern fuel injection system. And it uses high pressure hydraulic oil pressure working underneath a plunger to move your high pressure fuel injection plunger upward. And they're calling them a hydraulic piston here, right? So on the lower part you have a control valve that will allow hydraulic oil under a large piston, which is at least about 6 times larger than the high pressure pump plunger. And that force moving upwards will move the plunger upward and deliver fuel through the high pressure pipe to the fuel valve or the fuel injector. Now, this is what controls the flow of this hydraulic actuating oil is the ELFI. And this ELFI valve is a proportional. So they can control not only the start of the movement of the plunger and end of the movement of the plunger to start and control your effective stroke, but they can very, very readily change the rate at which the pump plunger will move. And this gives them the ability to rate shape. So they can control injection flow rate throughout the very short time period that injection occurs. And injection is typically a very, very short time period that actually takes place to inject this. But with computer controlled, this is one of the primary ways that they're going to be reducing emissions, particulates, and it also affects NOx. So electronically controlled engines can significantly reduce emissions without adversely affecting fuel efficiency. And the older Burmeister-Wain mechanically controlled MC series engines can be retrofitted to meet Tier 2 regulations through modification of the fuel injection equipment. And this is transient and low smoke practically disappear on electronically controlled engine. Now, smoke in different areas in the United States can be a very big issue, specifically when we're talking coming into Alaska and up to Valdez, and in some ports in like Los Angeles and San Francisco. And smoke the ship can be fined for producing smoke out of their funnel, and this has been successfully by various companies been successfully solved by switching over to electronically controlled either medium speed or slow speed engines. And it's quite important as far as the ability to operate in those areas without being fined. Well, we're going to halt this presentation at this time, and to finish this discussion, you will need to look at the second part of this presentation series. Thank you very much for your attention. Bye.